All right, hey everybody, I hope you can hear me okay. I'm trying something different. I thought I'd try and record off the document camera, so we'll see how this goes. All right, the topic is more of section 3.4. As you can see, we have three objectives in this video. Sketching f prime from f, that would be a review. Sketching f from f prime, that's new. And number 3, 2 justifications for concavity and points of inflection. All right, let's start our study of these three objectives by considering a pretty basic parabola. Let's consider y equals negative x squared. All right, we have an equation for this, but we're really working off the graphical approach in this lesson. So if you will, consider the downward opening parabola, y equals negative x squared. All right, objective 1 has us sketching f prime from f. So let's look at f prime, or y prime in this case. Okay. I know the equation is going to be negative 2x, but I just want to approach drawing the graph of y prime from understanding about the slopes on this graph right here. All right, as we study the regular graph right here, we see that the graph is increasing. Okay, the slopes are going from a very large positive number into 0. And to remind you, the slope values on the function plot as y coordinates on the f prime graph. So the y values are decreasing, the slope values are decreasing, okay, into 0. Okay, we reach our maximum, so our rate of change changes from positive to negative. So I should expect that I'm cutting through the x-axis. It's an x-intercept. Notice that the slopes here go from 0 to some larger negative number, if you will. So I would plot those in this fashion. So I'm hoping this is a review of sketching f prime from f. All right, look at objective 2. Okay, what if, and in the coming days, what if we were given a derivative graph and we were asked to produce a sketch of the regular graph? Let's say we were given a rate of change graph like this, and we want to produce a regular graph. All right, well, working off of y prime here, we would just have to know that the regular graph, okay, would be increasing because all these y values are positive. So when y prime is above the x-axis, the regular graph is increasing. When y prime is below the x-axis, we know the regular graph is decreasing because all these rates of change are negative. So we should expect the regular graph to be increasing, reach a maximum, slopes change from positive to negative here, and then start to fall and decrease. So that's one of the objectives, is looking at what we produced and making sure that we can go back and produce a graph of the regular function. All right, sketching f from f prime, that is. Okay. What you might find helpful is, some of you guys might, when you're working with a y prime graph, when you're working with the derivative graph, when you're working with a rate of change graph, you might find it helpful to collapse this, so to speak. Okay? And just real quickly, real lightly here, I'm going to collapse this graph, if you will, and then I'm going to erase it because I have another objective. And what I mean by collapse it is, look at all these values right here. They're all positive. Now I have an x-intercept at 0, so if I collapsed it to an f prime number line, okay, so this is a y prime graph, okay, let me make this a y prime number line. If I collapsed it, I'm just saying, take this x-intercept plotted to 0, okay, all these values are positive, okay, it would look like this on a y prime number line. Take these y values, which are all negative, okay, and put it like this. Sometimes for me it's easier to think about what the regular graph looks like when I work from a collapsed number line. So I know by looking at this that my graph of my y would be increasing, increasing, flatten out at 0, and that it would decrease. I don't know. Sometimes the interpretation for me is more obvious from a collapsed slope or number line graph here. It's up to you. Okay, the bad thing about this y prime number line is it really doesn't talk to you about the concavity. Okay, that's all. It just doesn't speak to you about the concavity. Okay, more about that in a minute. So I'm going to go ahead and erase this. Okay. All right, we do know that through the process of differentiation that this derivative would be negative 2x, and that does confirm with my graph and what I see. But I don't have to rely on an equation if I know the skill of producing f prime from f. All right, let's continue. What about if I wanted to know something about y double prime? Okay, well, what is y double prime? Well, it's the rate of change of the rate of change. So that's the second derivative. Okay, so again, to produce y double prime, I'm going to do the same thing I did to get y prime from y. Okay, so producing y double prime, now, yes, I know how to find the derivative. I know what I'll get. Okay, but I want to go from the perspective of how do I sketch it if I don't have an equation. All these rates of change here are negative. And so it looks like, because I have an equation, it looks like the slope of this graph anywhere is negative 2. So no matter what x I choose on the slope graph, I'm going to be down here at negative 2. I'll just label this negative 2. So the slopes are all negative 2. I have a constant rate of change. Okay, so this is x and this is y. I have a constant rate of change here. So that's just the nature of this graph. So we know that y double prime is negative 2 because I have an equation, etc. here. Okay, so sketching a derivative graph from a given graph is certainly one of the objectives. Okay, let's look at now objective 2. What if we were sketching f from f prime? Meaning, what if I was given this graph and asked, what is this the derivative graph of? Well, as I observe what's happening here on this graph, I see that every rate of change is negative. Okay, these are the y values, the rate of change on the previous graph. So if all these y values are negative, that means the graph before this, okay, would all have negative slopes, and they're the same negative slope. So I should assume that every single one of these y values is the same slope here. I should just expect that it's going to be a linear function. Okay. All right. Now let's move towards the third objective, and that's to talk about concavity. All right. We can clearly see that the graph of this function right here, the original function, is concave down. So now I'm talking about concavity on the regular graph. This graph is concave down on negative infinity to infinity. It's clear to see. We can see that this whole graph is concave down. Now what makes this graph concave down is the second derivative is negative. So let's zip on down to the second derivative, and it's clear to see that this whole function right here is negative. So I can say this is concave down on all real numbers because, I'm sure I would have left myself some room here, because f double prime on any x, okay, is less than 0. And we've seen that. We've explored that. Okay. Okay, but I want to talk about an alternate justification for concavity. Well, instead of talking about the second derivative being negative, okay, we can talk about, let me put or here, or because f prime at any x, well, let's look at f prime. What's f prime doing on its graph? Well, you guys can see that f prime is decreasing. Okay, the values of each and every one, as we move from left to right, each and every one of these values is getting smaller and smaller. So my graph is decreasing, hence every slope is negative. My second derivative will be negative. So if my second derivative is negative, then that must imply that the derivative before it, or the function before it, in this case the first derivative, was decreasing everywhere. And that's what's happening. When the rate of change graph is decreasing, I'm not talking about positive or negative, that's reserved, positive or negative is reserved for the second derivative. When f prime is decreasing, then that tells us the regular graph itself is concave down. And another way to think about it is this. Okay? If this graph is concave down, work your way from left to right. Notice what the slopes are doing on an interval. As I work my way from left to right, I'm not just looking at a slope at one particular x value. I'm looking at a whole bunch of slopes in a whole group. This slope right here is positive, large. This slope is still positive, but decreasing from the previous one. This slope right here, okay, is getting close to 0, decreasing. Okay? So when we're looking at these values and comparing them on an interval, we can see that the values of these slopes, okay, are getting smaller and smaller. And if that's occurring, what's happening is, okay, you're sweeping out a graph that is what we call concave down, like a frown. Okay? So, or because f prime of x is decreasing. So again, thinking about this, if the second derivative is negative, if the rate of change of the rate of change is negative, that has to mean that the graph before it has to be decreasing for me to have a negative slope. Okay, let's look at y equals x squared. These are just some basic problems that are easy to kind of put our minds around for our topics that we're looking at. Okay, y equals x squared. I think I'm going to try and leave myself with a few lines here for this one. Okay, let me produce a y prime graph. Not because I know this is 2x as a derivative and that 2x looks like this, but because I'm looking at how to produce f prime from f. These rates of change are negative going into 0. So as I bring them down here, negative y values going into 0. Negative y values means you have a decreasing graph. I have a minimum, so I should expect my y prime values to change from negative to positive, negative to positive. Okay, so the graph goes up like this. Okay, so let's continue practicing that. I'm going to go to the next derivative. It's kind of like starting all over. Okay, how do I produce a slope graph, a rate of change graph, or this rate of change graph? Well, just notice what all the slopes are doing. They're all constant. They're all about the same. And because I have an equation, and I can say this is 2x, I would know for sure that the next derivative would be 2. What if I didn't know that this was 2x and it was just a graph? Well, the only thing I can do is just imagine or guess what I think this number would be and plot it as a y coordinate. So I'm going to call this 2 here. Notice that the second derivative is always positive. Well, if the second derivative is always positive, what does that tell us about the regular graph? Well, it tells us the regular graph is concave up everywhere. Okay? So, kind of skipping over objective 2 here and going right to the justifications here. If we have a second derivative that's positive everywhere, then we should expect that this graph is concave up on all real numbers. Concave up on all real numbers. So what's our justification? Because we can clearly see y double prime, we want to use that, or f of x if we're going with the f notation, that any x is positive. Or you don't have to do both, just one, or maybe for some reason we have this graph first and we don't need to graph this one, or we can say because the f prime graph is increasing. And think about that. If f prime is increasing, every rate of change is positive, it's going to make your second derivative positive. What's the preferable justification? I think I've seen the preferable justification be the one from the first derivative perspective. Okay? So when we talk about concavity of a graph, we can justify concavity through the first derivative or the second derivative. But it's a good idea to know both justifications because you don't know how they're going to present a problem to you. Graphically, okay, from the first derivative or second derivative. Okay. All right, let's look at one more. Hopefully with the time we'll be okay. One that's a little more interesting perhaps. Okay, let's look at the x cubed graph. Very clear to see what's going on with concavity. The graph is concave down to begin with, up until 0, and then the graph turns to be concave up. So let's see how that looks in the f prime graph and the f double prime graph. Okay, so we're looking at the concavity idea here. Okay, let's get the f prime graph. Well, we know it's 3x squared, but if I was trying to produce the graph without knowing that, notice that all the rates of change are positive except for right here at its flat spot. The slope is 0 at x equals 0. The slopes are great, and then they come into a 0 slope. As we leave the 0 slope, the slopes start to get larger and larger. The tangent lines get more steep, so what we do is we create this graph right here. And we knew that because we knew the derivative would be 3x squared. Okay? All right, so we're accomplishing a few objectives. Let's look at the rate of change of the rate of change. Okay, if I wanted to produce that graph, because I have an equation, I can certainly differentiate and produce it, but let's just try and practice our skill of producing a rate of change graph. So negative slopes into 0. Pretty steep negative slopes into 0. Okay, I have a minimum here, so I should expect to have an x-intercept where my slopes change from negative to positive. Okay, and then I have positive slopes, and they're getting larger. So this derivative would be linear here in this case because we started with the cube, etc. So we have 6x here. Okay. All right, so let's look back at our original graph. Remember what we said here. We said that we knew that this graph was concave down by the visual from negative infinity to 0 because two arguments. Because we now know that f double prime from our graph, f double prime is less than 0, second derivative is less than 0 tied to concavity being downward, okay, on that interval. That satisfies it. You're done. Or, not both, okay, or if it's the second derivative is negative on that interval, it must be because f prime, let's look at it, f prime is decreasing on the interval from negative infinity to 0. Negative slopes here mean the graph before it's decreasing. Yes, it verifies the f prime graph is falling. Okay. All right, let's look at concavity upward. Concave up, 0 to infinity, because the second derivative is found above the x-axis, because yes, f double prime is a greater than 0 from 0 to infinity. Okay. Or, not both, okay. If it's going to be concave up, okay, think about the graph being concave up here. Okay. That must mean that our slopes on an interval are increasing. Our f prime values are getting bigger because f prime is going up. Okay. We'll have more practice, but hopefully that kind of lays the foundation for what we're going to need.